Hi folks, and welcome to another episode of Open Analysis Live. This is our first episode in 2018, so Happy New Year to everyone. I hope it's going to be a good episode. What we're actually going to do today is we're going to do sort of a two-part video series for a user question somebody left in the comments. The Beckeb wanted us to take a look at 3 samples that they had that didn't run in their Cuckoo sandbox, and they want us to explain a little bit more about how to identify anti-VM techniques using IDA. So that's what we're going to do today, but these samples are packed. So what we're going to do is we're going to have 2 videos. This is the first video in which we show you how to unpack stuff. We're going to show you how to unpack stuff quickly using some static methods, some Python scripting. And then the second video, which I will link below, once it's ready, once it's out, we will actually look at the unpack sample and find out why it didn't run in the sandbox and how to patch it so that it'll actually run. We have the 3 samples pulled up in hybrid analysis. Now I've actually already looked at these files in IDA, and I can tell you that they're all pretty much the same malware. So I'm just going to analyze one for this tutorial, but they're all pretty much the same. Let's pop over to our VM here, and I'll just show you what this commenter was mentioning where it actually doesn't run in the VM. Let's take a look at its behavior first before we look at it in IDA. So I have a XP VM set up here, no networking, and I'm going to turn off shared folders just in case something weird happens. Anytime I run something new now, I like to turn off share folders just in case it's ransomware. Now I know that this isn't ransomware, but it's just good practice to do that. And I'm going to rename Process Explorer here to fun.exe so that if there is some check for Process Explorer, it won't find it. Okay, so let's run our sample here and we'll watch in Process Explorer and see what happens. So we double click it, we can see it's running here. It starts a second process. And it shuts down the VM. So that's what the commenter was probably seeing. They were probably running this, and as soon as they ran in the sandbox would shut down. Right? The VM would shut down. So that's what we need to take a look at. Now, hopefully you guys caught it before the VM shut down. It did start a second process, so we know this is probably packed. We're probably gonna have to unpack something to get at that second process. Now, some of the astute among you are thinking, well, there's ways to stop your VM from restarting, and then you could probably just dump that second process. There are, but what I wanna do today in this tutorial is show you guys how to do some nifty stuff with scripting in IDA. So I figured I'd take the chance to show you guys how to unpack stuff statically with no debugger with some scripts. So let's pop over to our IDA instance here. Okay, so we have our file open up in IDA here, and let's take a look at the exports. There's one for start, and then the imports. There's lots of nice imports here, but right away I see something that I talked about in another video that kind of tips me off that something's not right here. See, there's only a tiny little bit of code up here that's been identified as code, and there's a giant section of data. So if we sort of pop over to this data section, we can see there's a whole bunch of garbled stuff in there, and our code section is over here. We're thinking right away, yes, it's probably packed. So that matches up with what we saw with Process Explorer, with this process starting another process. What we need to do now is figure out how this data stuff here is unpacked. Now, let's take a look at what they have in start. Actually, it's not start. We want to go to WinMain here. So in WinMain, we start out. We have our little function set up here, and then we have okay, all right. So this looks like just garbage. It looks like they've inserted, the developer has inserted a bunch of these move-al junk statements to try and make it difficult to read the assembly. I'm not going to use the decompiler for this tutorial because I know a lot of you don't have access to it, and it's, you know, it does make things go really fast because you can just kind of see a high-level view of the code very quickly, but I'm only going to use the disassembler for this because I want you guys to be able to follow along at home. With the disassembly view, these junk statements actually make it really hard to read the code here. You can see there's just tons of these sections. So here's some like useful code, and then there's another blob of this garbage here. So what you can do to try and make this code a little bit more readable is you can actually highlight these sections of garbage here. Just grab this section of garbage here. You can go to view, and you can hide this thing. Go down here and hide it, right? So we can hide that, and then if we go down here and hide this next garbage section, which is huge. Okay, so as we start hiding this stuff, we can see there's this starts to make a little bit of sense here, right? So if we do some magic of video here and we just do a cut. So now that we've hidden some of those, we can see that the code starts to become readable. So we can see here there's some stuff being set up for this call here. Let's call it the set error mode. You know, this pretty standard stuff. I don't think there's anything really unique here. There's like a file name being set up, some buffers, etc., etc. But the thing is, you can't just go through and manually hide these sections because there are hundreds and hundreds of them throughout the entire PE file, and it would take you way too long. So this takes us to our first sort of step into talking about IDA scripting. Now, this isn't a tutorial on how to actually get started with scripting with IDA. I'm going to put a link to Alexander Hanel's book about IDA scripting in the description below. It is pay what you want publishing, so you can actually pay nothing for it if you want to, but please pay something for it. It's a great book, and it'll kind of give you the introduction to IDA scripting that you'll need to understand this next part. But what I will do is I will kind of go over the script that I use to auto hide all of this junk code. So I'll kind of do a high level view. Now, I will also link that script on my GitHub so that you guys can go and take a look at it. And between that script and Alex's book, you should be able to make good use of it. Hopefully you can reuse it for other junk code hiding that you might need to do yourselves. Okay, so let's take a look at the script that I built. We'll just use VI for it right now. This is an IDA script that's on my GitHub, and I actually originally took the code from this guy over here, who actually has a lot of like really cool tools and stuff on his GitHub. Definitely check that out if you are into IDA scripting or IDA tools at all. So here's our normal imports here, IDA utils and IDC, and you'll see that we've prefaced all of our calls with either IDA utils or IDC. What we're doing here is we're going to loop through all of the segments. So these are each one of the PE segments. Then for each one of those segments, going to loop through all of the heads. What heads mean are all of the sections that IDA knows contain the start of an instruction or the start of a data segment, etc., etc. So these are all the starts of anything interesting for us, basically. That's the way to think of it. And then we're going to loop through all of those. We're going to check if it's code, and if it is code, then we're going to get the mnemonic for it, and then we're going to start our little logic tree here. So if the mnemonic is a move, then we're going to check to see whether the first operand is AL. And if you guys recall, in the junk code here, it's move AL and then some number. So what we're doing now is we're checking each one of the heads known to IDA to see whether they contain move AL. And if they contain move AL, then we start a counter for the junk counter, basically. Once we fall into a condition where we don't meet either one of these conditions, where there's no move AL, then we pop down into njunk. And in njunk, what we do is we check to see whether we have at least 4 consecutive move AL statements in a row. Now, the thing about this is that move AL moves a value into AL, the lower byte of the EAX register. Now, you would never have 2 of these calls in a row because you would just be replacing the byte that you moved in the last call. It makes no sense. But sometimes I thought maybe for compiler optimization, there might be some crazy situation where there are 2 or 3 valid ones in a row. Probably never going to happen. But I figured at 4, if there's 4 in a row, it's almost definitely going to be one of these junk runs. So we only hide it if it's more than 4. And if it's more than 4, we add the position of the start of this junk run and the length of the junk run to a nice dictionary here that we call hides. Now, once we've done running through all this, we just run through hides through the dictionary. And for each one of those addresses where we found a junk run, well, we basically print out to the command line to tell us what we're doing. So we're hiding this range of bytes. And then we use del hidden area, which means to remove any hidden areas in IDA. So we just remove it so that if there are any hidden areas, we unhide them. This allows us to rehide them. And then what we do is we use hide area starting at the first position of the junk run for the length of the junk run. And then we actually add this little color code here to show us that we've hidden that area. So let's pop over to our IDA instance here and we'll actually run that script. So we can just run script file, run hide.py, and you can see what it's done is it's hidden all of that junk code and replaced it with this little highlighted line. And what you can do if you want to show the junk code is you could just right click on that and you could do unhide and it'll show the junk code for you. But by running this script, you can see we've made this way, way easier to read. We can see what's going on and we can kind of move on to the second part, which is to actually unpack this PE file. So now that we've hidden all that junk code, let's move on to another trick that I want to show you guys here. So remember I said up here in the view of the PE file, so we can see there's a tiny block of code here and then there's some data here. Now, because I am almost positive that this is a packed file and I'm pretty positive that this giant blob of data contains the actual packed file, a very quick trick to figure out if you can unpack this statically is to locate the beginning of this data section here. So we'll just kind of scroll up until we see a reference to it. So right here, there's a reference to this data section and it's the last reference for quite a while. It looks like there's quite quite a bit of binary in there. And then just jump to the reference and see where it's actually used in the code. So we're going to name this blob1, I guess. And we can see how it's actually used in the code. Now, here's something interesting. The reason why we're doing this is because we may be able to actually identify the decryption function or the unpacking function without having to run the code dynamically at all in a debugger. Now, I know, because I already looked at this, I know that that's the case for this file. It doesn't always work like this. It's just a happy coincidence. I mean, I chose this file for this video for this reason, but it's always worthwhile to do this check because you might get lucky. And if you get lucky, it's going to save you a bunch of time. Basically, all we do is we just go to our data section here where we see the big long blob of data. We scroll down till we see the last reference. So this is referenced by code somewhere, right? So here's the reference in the code until we see the last reference for a while. So, you know, it looks like this references to a bunch of binary. And then we hop to the actual reference in our assembly and check it out and see what it's doing. So in this case, we're pushing it onto the stack as an argument for this function right here. And it looks like, here's where things get interesting. It looks like we also push on something that looks like it could be the size of that blob, right? That would be a realistic size of this blob. So anytime we see something like this binary blob being pushed as an argument to a function and what looks like maybe the size of that blob being pushed to the function, we should definitely check that function out because it might be a decryption function or a deobfuscation function. So actually, let's just name that maybe decryption. And we'll pop into it and take a look at it. So, and again, I want to remind you guys, everywhere you see this like light yellow line here is hidden junk data that our script has hidden for us. So without running that script, this would have been really hard and frustrating to read because this would have been full of junk code. But now that we've hidden it all, we just have these nice little yellow lines and we have actual code that we can read. So let's pop back here and just see what the arguments are. So the first argument is the blob and second argument is the length. So let's pop in here. Let's rename these. Name arg blob and arg4. 4 is just one D word below, so it's actually the second argument. Name arg blob len. Again, we don't really know that's what these are, but I'm pretty certain that's the length of the blob. You know, it stands to reason that it is. This is called file name because it must be referenced as a file name somewhere else in the assembly, and IDA has been helpful and given that a name. And then we have our last argument here, argc. So let's go down and see where arg blob is used in the code here. So we can see here we have a nice loop, it looks like. Yeah, okay, this could be decryption, right? So we have a loop, we're using the blob, we move the address of the blob into EAX, we add 1C to it, 0 into 1C, so maybe this is a counter. Do we increment 1C, ECX, and then move it into 1C, add ECX1? Yeah, so this is our counter here, so let's rename that as a counter, or our counter, or actually let's call it a blob pointer, blob or blob counter. So it must be giving the offset in the blob. So, 1, 2, 3, 4 for the bytes, 1, 2, 3, 4, et cetera, et cetera. So what we're doing is we're moving the first byte of the blob into CL, moving that into buffer. What else are we doing here? argc, interesting. Okay, so we're moving argc and we're subtracting argc from the byte of buffer. So we probably need to know what that argc is. Let's go back and see. So that's our fourth argument on the stack, argc. So we have arg blob length, arg file name, and the last argument, which looks like it's going to be a char. So let's pop back to the references. Oh, there's two references. Okay, well, we're looking at the first one here. And so that would be the first push, which is, ECX, the first push. So remember arguments 1, 2, 3, 4, fourth argument, ECX, and let's see what that is. So we know that it's a char. It moved into CL from var 9, so let's rename that as var arg char, and we'll see where that comes from. Okay, moved into EAX and compared to, what is that? Press R to turn it into ASCII character. So or press R to reveal R. So if you press R on the keyboard in IDA, it'll actually turn the immediate value into an ASCII character. It'll try to display it as text. But in this case, it actually turns into be an actual R. Interesting coincidence. So what we're doing here is we're comparing whatever our char is, which is the fourth argument to that function, with R, and if it matches, if it doesn't match, we jump down here. If it matches, then we jump into the function that we were just looking at, I think. Yes. Okay, so that means that argchar must be R in order to get into this whole function. So it's going to be R for that function there. So I know that it's probably maybe used at a different place, but we're just going to call it, we're just going to add that label to it right now so that we don't forget that is actually an R in this case. Now, again, it might be used elsewhere in the code and where it's not an R, but in this case for this function, it is an R. So I'm going to temporarily put that R on there, and then we'll come back down here. So we know that at this point, this is a R. Okay. So if we pop into here, we know that this, in that case, at least when that's called, so remember there's two calls to this function. So at least in one of the calls, it's an R, which is this argc name argchar R. And again, it's not always going to be an R. You can pass any ASCII character into there, but in this case, it is an R. So what they're doing is they're actually subtracting R from, where were we here in our loop? So here's our sub, edx is char R. So we move R into edx. We move buffer into EAX, and remember buffer contains the first byte of blob, or whichever byte of blob is pointed to by blob counter, which we saw down here is incremented by 1. So it looks like they're looping through that big binary 1 byte at a time, and they are subtracting R from each one of those bytes. And then what do they do with it afterwards? They move it back into buffer. They move that into ECX. What else are they doing with it? Okay, interesting. So they actually compare the counter with 2F0 hex and with 2FF hex. And if it matches, so if it's in between 2F0 hex and 2FF hex, so yes, we go to rand, so we create a random number and we move that random number into buffer. Interesting. Okay. So we either subtract the ASCII value R from each byte in the buffer, and then that's what's left in the buffer. Or if the buffer counter is between these two values, we generate a random character and move that into the buffer. So far, so good. What do we actually do with the buffer? Okay, we write it to a file. So here we have write file. That must be where the file name comes from. Yes, file name. And it looks like we write the buffer, write file. Let's pull up write file in MSDN, and we'll just see if we can't get those arguments straight. I think I know what they are off by heart, but I'm just going to double check here. And let's take a look at these arguments. So the first argument is the file, then the buffer, number of bytes to write. Number of bytes are actually written over, I don't know what overlapped is. So the first three arguments are probably going to be the most important. So here's the file name that they write to, the buffer that they write to, and the number of bytes to write. So let's pop back to our IDA instance. We always know that argument 1 is the last one pushed. So that is the file name, as we already knew. Then the other push is the buffer, which we kind of suspected. And the last push is 1 byte. So here we go. Here's the whole function all in one, I believe. Yeah, the last thing is just to increment, and then we finally go up here and they just check against the blob length. They check the counter against the blob length, and once you've exhausted the blob length, you pop over here and I think you exit. Yes, you do. Okay, so here is the function in a nutshell, because we're gonna have to replicate it in Python, so we better talk through it one more time. We basically take the blob, we iterate through it 1 byte at a time. For each byte we subtract the ASCII value R, and then we keep that in the buffer. If the counter that's iterating through the buffer is between 2F0 and 2FF, we, instead of using the buffer byte subtracted with R, we just use a random value. And the cool thing about this is that a random value could also be the value that's already in the buffer. So we don't even have to implement this random value thing. We can just do subtract R from all the values because it could be a random value. So let's actually implement that in Python, and we will dump this blob out to a file, and then we will use Python to decrypt it and see what it is. So let's actually dump the blob out first before we implement the algorithm in Python. And to do that, let's pop back to the call to this function, first one here. And so we know that this is the address of the blob, and that's the length. And if you guys remember from another video, I have a script which I can just import here, Python script called Memdump. So I'll just add the Memdump file here, and I'll just call it Memdump, and the first argument to Memdump is the address of the blob. So let's see what the address is here. And the second argument to Memdump is the length of the blob. So let's pop back here, and the length is this right here. So let's paste that in here, 0x length. And then the last argument is the file that we want to dump it to. So I'm going to dump it to my Z drive where I have mounted the temp folder for my Linux machine. Okay, and success here. So we have that dumped out to our temp drive. So let's pop over to our command shell here and make sure that it's actually dumped out. So here's our command shell, do an ls. Here's blob1.bin. So we actually dumped it out successfully. And for this one, because this is a pretty simple algorithm, instead of actually writing it out in a file, I'll probably just use the interactive command line interpreter for Python. So Python, and then I'll open up that blob file and read it in with open read binary data equals fp.read. There we go. So if we dump out some of this data, let's just make sure that it's right, 100 bytes of it, just to make sure. There we go, it's good. And then let's take a look at our algorithm. So let's give it a string to output to, and then we'll do our iteration through the binary, just like they have in the code that we saw. So for byte in data, so byte is going to be each byte in data, and we are going to subtract R from it. So let's do ord to turn it into a number, byte, subtract ord of R. And now here's a trick. Because we know that this is a byte in IDA, it's a byte type, we have to AND it with 0xFF so that we don't have an overflow situation with subtraction. And then let's turn this back into a char, and then let's add it to this out. Plus equals out. Okay, and then let's take a look at the first 100 bytes and see if we actually got something useful. No, we didn't. So let's pop back to our IDA and see if maybe I missed something in this algorithm here. So let's go into the decryption routine. So we'll go down to the subtraction. So remember we have the R into EDX, buffer into EAX, sub EDX from EAX, move that into the buffer. Oh, there's no subtraction. I just jumped right over that last time I looked at it, didn't I? All right, so we move the buffer into ECX and we subtract the counter from ECX. Okay, I see there's another step. So they not only subtract the value of ASCII R from the byte, they also subtract the counter number, or the iteration, or the position of the byte, I should say. That's the best way to describe it. So 0 from the first byte, 1 from the second byte, etc., etc., etc. Okay, this is definitely going to be a little bit more interesting. Let's pop back to our Python shell here, and we'll see if we can't implement this correctly this time. So for this one, because the counter can't be the byte, because the counter needs to be the iterator number so that we can actually subtract it, let's try for I in a range 0 to length of blah, or data, I think we called it, data. And so now we have an iterator, and then we can use the same statement here. Oops, I forgot to zero out. That's always a problem. Let's zero out. So we make our string null again. Let's try this a second time. Now again, we can reuse this same statement. We just need to add something extra to it. So the first thing we need to do is byte is no longer byte. Byte is actually data at the pointer that we're using now, the iterator. So data at I, and then we also have to actually subtract I from all of this. So let's see if we have this right. We have the byte, which is pointed to by our iterator I, subtract the value of R, subtract the actual value of the iterator, then we AND it by 0xFF to turn that back into a char, just in case there was an overflow situation. Then we actually turn it into a char using the char command, and then we add that to the string. So let's see if this works. So let's print out those first 100 bytes here. Oh, I see, I need to actually do out. I wasn't saving those bytes into data, I was saving them to out. So let's print the first 100 bytes of out, and hopefully we got something here. Hey, there we go. That looks good. So there's our MZ header for a PE file. There's this program cannot be, etc., etc. So it looks like our little decryption algorithm works okay. So let's actually write that out to a file now. So let's with open, let's call it blob1 decrypted.bin. We're going to write some binary to it, and as fp, as fp, and we are going to fp.write. Okay, so we should have that saved and we can open up in IDA. So let's take a look at it. Okay, so we have our file opened in IDA, and can you guys spot something that's kind of not right here? Looks like it's actually a DLL, and if we hit on exports, yeah, it's definitely a DLL, and there's one export here, PWT. So if you remember really quickly when we ran Process Explorer and we ran this file in our VM, we saw that it actually started another process, and if you guys remember very quickly, that process was definitely not run DLL. That was definitely a executable process. So maybe there's some injection, but I have a hunch that perhaps this DLL is related to this, but it may not be the actual unpacked executable. It may have some other purpose in the binary. And if you guys recall, if we like close this up here, go back to our packed file here, and if you guys recall, the decryption function here actually had two references. So here's a second reference to it. And if we hop over here, there is it looks like another blob. Another blob is being decrypted. So why don't we extract that blob and see if that's an executable and not a DLL? And if it's an executable, then it might be the PE file that we're looking for. Okay, so let's use the same technique that we used to dump the other file. I'll just use, it's probably still in the history here, and it is. So we're going to call this blob2, and we are going to put the size is 5 and a bunch of zeros. And the offset here, there we go. Dump it out. It's dumped. Good. And we can just reuse our code and our command shell here to decrypt that blob as well. So we'll just reuse the previous commands here. All right, so that's also PE file. So far, so good. Let's dump that out to blob2 decrypted and see if we can't get an exe out of it. Okay, so we've opened up blob2 decrypted, the second PE file that we dumped out statically from the packer, and this one is actually an exe file. So I think that this is the payload that we need to look at for the second video, and having done this before, I know that it actually is. So stay tuned for video number 2, which when it's out, I will link in the description below, where we will actually look at this unpacked payload and find out why it's not running in the VM, why it's shutting down the VM. And hopefully that's kind of interesting. I'd like to say thanks to everyone who is sharing our videos. Remember, if you haven't subscribed yet, make sure to subscribe. Hit that notification button, the little bell, so that you get a notification every time we post a new video. One new video a week, every week. We'll try and keep this up for 2018. And remember, keep exposing the mechanics behind the malware and stay curious.